Uh, okay, nice. Okay, so I'll talk about two relatively recent projects. They're both kind of around the computational benefits and limitations of transformers and state space models. Okay. So there'll be two parts to this talk. The first one is kind of a direct comparison studying the power of transformers versus state space models for sort of language modeling tasks and kind of what are the things that it can do and cannot do, and sort of trying to compare them. And the second part of this talk will be on specifically on transformers and Lang generalization and transformers, and kind of a more recent paper that we put up on how we can get Lang generalization with transformers. Um, just to kind of, motivate this whole discussion, so we start with a, big general question, which model we should use for doing sequence modeling. And I guess in the 90s, you'd have asked this question. The answer was some sort of recurrent model or LSTM. From the 2017 and on, transformers are kind of dominating the landscape of architectures. And, this is like almost all of the big language models are using some variant of transformer architecture. And very recently, there's this family of models called state space model, been very popularized by the Mamba model, and this is kind of like another alternative that maybe is somewhere in between the transformers and recurrent models. And we want to understand, what should we use out of these models? Are we kind of moving forward to the state space models, staying with transformers? Kind of what are the costs and benefits of these models? Um, there's like one way to answer this, is just, look at the cost of running both architectures. So if we're analyzing the cost of running a transformer-based model, for some sequence length L and model dimension D, the complexity of running the transformer grows linearly in terms of memory. And the memory would grow linearly with the sequence length, and the compute would grow quadratically. Um, State space models, on the other hand, have sort of like fixed state or memory. So when we're running the state space model, the memory complexity of the model stays the same. It doesn't change with the sort of with the when increasing the sequence length, and same goes for the compute. So we're basically the per token compute and memory are constant, which is a very nice property, because if we want to do very long context language modeling, we don't have to kind of worry about the memory blowing up and the computational cost increasing. But of course, we don't only care about the cost of running the model, we also care about performance, and there's like various different ways to measure performance of these models. So one obvious way is to look at the perplexity of the model. So we're training the model on some data set, maybe a natural language data set from the internet, from kind of some internet source. And we're just measuring the loss of the model and comparing these different models on kind of, flop versus perplexity. And there we can see that this very recent state space models, Mamba model compared to Transformer, are doing quite well. So they can catch up, at least in some settings and some scales, they can catch up with Transformers, even do a bit better. Another way to measure performance is look at downstream tasks. So not just look at the loss, but actually kind of write down the tasks that we care about. Maybe it's a mathematical reasoning task, maybe it's just common sense reasoning, other type of tasks, and just measure the performance of the different models trained on kind of the same data set. And here we can see too that at least under some evaluations, the Mamba model is doing quite well, and comparing this to the transformer model, it's doing even a little bit better. So, just looking at these, maybe it seems like, we have a more efficient model. It gets better loss. It gets better downstream performance. Maybe this is really the thing that we should use. And then the approach that we took in our work is come up with some synthetic tasks. So this would be kind of characterizing the sort of building blocks that we want the model to be able to do. And instead of measuring it on right away on downstream tasks, we're going to kind of construct the building blocks or the tasks that we want the model to be able to solve and see if the model can be trained to solve them. And this would be kind of the main measure of differentiating between the model. So, just in kind of a general note, and why do we want to use synthetic tests, or why are they useful in this setting? So first, it gives us a very clean experimental setup. So we have kind of complete control over the entire problem. We set it up. We can not put any noise into the problem. We can put a little bit of noise. And this is something we can really understand fully. And this also allows us to do some math because we have like the entire kind of definition of the problem. This would be something that is kind of mathematically well defined and will allow us to do both kind of upper bounds, so prove that some model architecture can solve the task, or lower bounds, prove that another model architecture cannot solve the task. So this kind of nice thing about synthetic tasks, and these will kind of come back in like different parts of it. So the first paper that I want to discuss is a paper on comparing transformers and state space models. We call it Repeat After Me. And the main message of this paper is kind of understanding the power and limitations of the different models for kind of copying and retrieval tasks. So we'll start by focusing on a very simple synthetic task. It just requires memorizing the entire context. So I give you a sequence of tokens or words, and you just need to repeat it. Just copy the kind of sequence of input tokens. And you can think of this as kind of an essential building block for a lot of tasks that require kind of copying parts of the input and kind of putting this into the answer. Another type of task that is very similar is retrieval or kind of associative recall. I give you a sequence of tokens and you need to give me back a part of it. So it's kind of like copying, but a small piece of information from the input context. So these would be the kind of two synthetic tasks that we'll discuss in this context. To start with some theory, to understand kind of the capability of transformers and state space models and doing copying. So we'll have a dictionary of tokens or words. We're giving the model a kind of input prompt of length L, and the model needs to just reproduce this length L context. And the models that we're training is kind of like standard autoregressive models. They take a sequence of tokens and just produce the next token in the sequence. So we start with kind of giving the input of a sequence of tokens and generate the next piece of information. So the kind of positive result we have for transformers, we're showing that a small transformer can perform copying of strings of length L under a specific condition that there is no repeated n-gram in the string. So by repeated n-gram, I mean that we get a sequence of L tokens, and there is no repeated string of length n within the sequence of tokens. We can show that a transformer can copy this input with the dimension or size being n log d. So n is the length of the non-repeated n-gram, and d is the size of the dictionary, and the length of strings they can copy is exponential in this n. And since, if we're sampling from a uniform distribution, a string of L tokens, the probability of getting repeated n-gram decays exponentially with n. And this means that depth to transformer of dimension is logarithmic and the sequence length can copy strings with smaller, right? So we only need the size of the transform to grow logarithmically with the size of the string, which is just to say that a relatively small transformer can copy strings of exponential length. Now, the way that we're showing this positive result, there's maybe different ways to construct a transformer that can do copying, but we're interested in a kind of specific construction that will kind of track the way that we actually understand that transformers are doing copying, and I'll try to convince you later that this is actually how transformers succeed to do copying. So basically what we're showing is the transformer can implement what we call an n-gram lookup algorithm for copying. So let's say we get a sequence of tokens as the inputs to the model. Now we're storing a kind of lookup table or a kind of a hash table for sequences of n tokens. So we're kind of hashing n-grams consecutively from the input. And for each n-gram, we're storing the token that came after it. Okay. And now when we want to do copying, maybe we succeeded to copy a few input tokens from the model, and now we want to understand what should be the next token that comes after the sequence that we already copied. We go to the lookup table, we'll look at the most recent n tokens that we just generated. We'll look this up in the table, and this kind of points us to what should be the next token in the string. And this way we can implement the copying mechanism. So note that this thing, in some sense, relies only on kind of like local position understanding of the tokens, and you don't need to kind of access globally different tokens based on their position. So we're not doing copying by looking at, pulling the first token, then the second token, then the third token, etc. This is kind of a different copying mechanism that has some benefits that I will discuss later. So one interesting thing to point out about this mechanism is somewhat a very kind of natural thing for a transformer to learn to implement. It really can be implemented efficiently using this kind of key query value retrieval mechanism of the transformer. In some senses, it's very similar to the induction head that's been studied in different contexts. But instead of doing induction head to retrieve a token based on only the last token, we're retrieving tokens based on the last few tokens, or the last n-grams. So this kind of like plays very nicely with the structure of the transformer. We can kind of implement this very efficiently with the transformer. So to show the theoretical result, and this will come back later, we're using a sort of variant of the alibi positional encoding that kind of allows us to do this n-gram hashing more efficiently. It's not to say that alibi cannot do this, but this is kind of a more natural way to do this. We're going to rely on what we call hard alibi, which is a kind of different variant of the alibi positional encoding, where we're sort of setting up the positional encoding to only for some of the attention heads only look at the few tokens, a few recent tokens, and kind of mask out all the history. So this was the sort of positive result for transformers. By the way, if there's any questions, you can feel free to interrupt, or I will pause every few slides for questions. Okay, so we showed the kind of positive result for doing copying with transformers, and we showed that transformers can do copying efficiently. Now I'll go to the kind of negative results and show that state space models, or more generally, any model that kind of operates recurrently in some hidden state cannot perform copying of arbitrarily long strings. So for us, state space models is a state space model is any model with kind of constant memory, so finite set of states. And we have this sort of an update rule. So each time we see a token, the state of the model changes. And this is the update rule that is denoted by U here, and we have an output rule. So given a state, what is the next token that we're predicting? So this is a very general way to model these state space models. We have like each token, we're updating the state, and we're outputting some token. And the only thing that we require here is that the state space is finite. So you kind of encode it with a finite set of things. And the negative result that we show is that for any state space model, we'll have an error that kind of goes to one exponentially with the sequence length when we're using the model to copy strings of length L. Okay, so the error is 1 minus the size of the state space, so the number of possible states, over d to the power of L. So it kind of goes exponentially fast to an error of 1. And the idea is, very simple. We want to be able to copy L symbols from the dictionary. You must be able to store them into this memory. And if we don't have enough bits to store this string, we're going to suffer from a high loss. Okay. Any questions about either this result or the previous upper bound for transformers? Okay. Okay, so this was sort of, two results on expressivity of the two models, one showing that transformers can copy and the other showing that stasis models cannot copy. But really what we care about is not the expressivity of the models. What we care about is whether or not they can learn to solve the kind of problem we train them to solve. So maybe there's, this kind of theoretical expressivity gap between transformers state space models. This means that if the kind of memory of the state space model is very limited, these state space models cannot copy. But, we can just increase the memory of the state space model to be, enough to store the input context. And then, there's no expressivity gap, or theory does not apply for like large enough state space models. Maybe this solves the problem. But of course, there's also the question of how can these models learn, or how fast they can learn. And this brings us from kind of the expressivity point of view to optimization. So here we don't have theory, but we do have a few experiments. And we're basically plotting, this is training different transformer architectures versus kind of recurrent architecture. So either Mamba or LSTM, training them specifically on the synthetic copying task. So we get just uniformly at random generate the sequence of tokens and train the model to just copy this sequence. And what we can see here is that the transformers learn this, depending on the positional bending, they learn to solve this task quite efficiently with a relatively small number of training steps. And interestingly, the Mamba model, if we take it to be big enough, eventually also learns to solve this problem, right? So there's no expressivity gap in this situation. But it takes it much longer to learn to solve the same problem, right? So it's about 100 times more slow compared to the transformer. So this really shows that even in the cases where we don't have expressivity gap, we're taking the model, the Mamba model, to be big enough, the optimization of this model is much worse, and it takes it much longer to solve the same problem. Okay. So next, okay, we show that there's kind of expressivity gap, optimization of transformer is better. What about length realization? So I'll go back to length realization, kind of the second part of this talk, but I think this point is also interesting to make in this context. So by length realization, I just mean that I train a model to solve a task up to length L. So it only saw strings of length L during training time, and I test it on strings that are longer than length L. And what I showed you is that transformers of size n can copy strings that are exponential in the size of the transformer, while state space models must use linear size in the input context to learn. And this just means that if we're taking the size of the state space model to be large enough, we're training it to do copying of length L sequences where the length of the sequence is roughly similar to the size of the stasis model. Both of these models can learn to solve the problem efficiently on the training distribution. But of course, if I increase the size of the strings that I want to use the model to use the model, I increase the length of the strings I copy with the model at inference time. So I ask it to do length generalization. State space models will fail very quickly just because when I'm increasing the size of the sequence, this goes beyond what they can store in the model. Well, transformers will succeed in copying much longer strings, assuming that they learn the kind of right copying mechanism. And we can also see this experimentally. Here we're training both transformers and state space models to do copying, but we're training both of them to copy strings up to length 50, and we see how they extrapolate to strings that are kind of longer than what they're trained on. And you can see that both both types of state space models kind of collapse very quickly and do not generalize beyond the input distribution, while transformer variants are extrapolating much better, and specifically with this kind of hard alibi with our new positional encoding, they can extrapolate to very long strings. So finally, we want to understand, in this kind of, again, synthetic regime, we want to understand what is the actual copying algorithm that transformers have learned. So I showed you this kind of n-gram-based copying algorithm, but, is this what the transformer actually learns? So to test this, we're feeding the transformer with kind of a different distribution than what it was trained on. So we trained it on just standard copying. And at inference time, we fit a distribution of copying strings where we purposely, kind of duplicate n-grams from the input strings. So we feed it strings with duplicate n-grams. And we can see that when we're increasing the n, so there's longer strings of duplicate tokens, the model starts degrading in performance. And if we have strings of length 8 in the context that are duplicated, the copying mechanism that generates completely breaks. And this sort of tells us that it's really relying on this n-gram hashing mechanism, because otherwise, if you're just copying based on the index of the string, there's no reason that having repeated n-gram in the input context would make the performance degrade, right? So it sort of tells us that this is really the mechanism the transformer implements. Any questions on this? Okay. So yeah, we're also testing the both models on retrieval-based tasks. So this is very similar to copying, but instead of asking the model to copy the entire string, we ask it to copy a small sequence of input tokens based on the kind of n-gram hash that appeared before. And we can see again that transformers generalize to longer strings much better. We see the opposite thing, and at least in some cases, when we put the retrieval key before the input context, right? So you can imagine that in some cases, I first ask the model what I wanted to retrieve and then give it the input context that I want to retrieve from. And this allows state space models to operate much better because they can kind of store in advance the thing that they need to retrieve. And once they see it in the context, they can store it in the memory. So this really is a task that you can solve with a fixed memory. And indeed, we can see that state space models do much better here. Okay. Okay, so moving on to kind of more natural experiments. So here we're taking pre-trained models. So these are not models that we trained. It's a Pythia suite of models, transformers trained on the pile versus the Mamba models, again, of like roughly similar sizes and trained on the same data set. And we kind of prompt it to do copying of kind of natural language strings. So give it a sequence of tokens and then ask it, repeated in like 2 or 3 sentences, then give it the first word in the sequence and ask it to complete it. And what the model does usually is just copy the string. And here we see again that the transformers are, doing much better at this task compared to the Mamba-based models. Um, Similarly, we're looking at retrieval tasks. So this sort of like phone book lookup task. I give the model this kind of fake phone book, so names and numbers, and ask it to retrieve the number of the person from the phone book. And you can see that depending on the number of entries in the phone book, as we kind of increase the size of the phone book, the transformers are doing much better than the snake-based models. Um, Finally, we're also, testing this as one kind of like more real question answering data set. We're giving the model an input prompt. And the task is, here's a paragraph from some text, and the model needs to answer some question about the paragraph. And we're kind of testing the capability of the two models to answer the question correctly. When we're kind of controlling for the size of the input text that we give to the model. And here again, we can see the transformers are kind of, consistently doing okay, even when I'm increasing the size of the input context, and the Mamba models sort of degrade in performance when the length of the paragraph increases. It's kind of like consistent with the previous one. Okay, so just to summarize this part, and then, feel free to ask some questions. So we showed this kind of separation result between transformers and state space models. We proved some expressivity gap on copying, showed some synthetic experiments that transformers can learn faster and also length generalize. And we showed that the pre-trained transformers can do better copying and retrieval, and also question answering with long text paragraphs. And of course, kind of looking forward, and this is already, there's a lot of literature around this. Maybe the kind of, next architecture would be some sort of a mixture between the kind of a hybrid model between transformers and recurrent modules. Okay, any questions so far? Okay. Okay, so this next work is kind of with a similar group of authors, is on length generalization and transformers. So now we're kind of specifically focusing on transformers and, trying to study this question of length generalization. What are the type of problems that transformers can learn to length generalize on? And I'll kind of go back to this copying mechanism. Will play kind of a major role in studying this problem and understanding this result. So again, length generalization, I mentioned this before. We have training distribution of sequences up to length L, and we want to evaluate the model on sequences that are longer than what it was trained on. So one example for this that's been studied a lot is multi-digit addition. So we're training the model, let's say, on adding two numbers of up to 50 digits. And now we want to test the model on longer addition problems. So, longer than adding numbers that have more digits. And this has been studied quite a lot. There's a lot of prior work to do, different, find like different ways to solve this problem with kind of different tricks, and the results are quite impressive. And you know, before kind of showing our solution, maybe to kind of motivate this whole field, maybe like two reasons that you might care about length generalization. One is, training on shorter sequences is just more efficient. So if I want to get a model that can operate on longer sequences of strings, but I, want to train it efficiently, maybe I don't have a lot of data with longer sequences, or I just want, to train the model more efficiently. It would be very nice to train a model on shorter strings and have it just, out of the box be able to operate on longer strings. That's kind of like a more practical reason to study this problem. Kind of from a more theoretical perspective, showing that the model has solved the problem, is able to also length generalize, sort of shows us that the model learned kind of the right function or the right solution. In some sense, if it learned to solve a problem, but it completely breaks out of the distribution, maybe this shows that the solution is found in some sense wrong. Maybe it memorized some things from the input distribution and just uses it, but not really kind of generalizing in a deeper sense. Okay. So one kind of major thing that we rely on in this work is the idea of having a scratchpad or chain of thought. So let's say that we want to do addition of, multi-digit addition. One way that, might seem natural is, instead of training the model on kind of these addition problems and immediately asking it to generate the answer, we train the model with the addition problem and also the kind of trace of the addition algorithm. So do the kind of multiple steps of the addition algorithm, first at the first digit, carry, et cetera, the same way that we would solve the addition problem if we didn't have a calculator. And, for some problems that are kind of, I guess, algorithmic or arithmetic in nature, it's very hard for the LLM to solve these problems directly. But if we break the problem into, the different steps that we need to execute, this makes makes solving this problem much easier. So one simple observation is that, if we look specifically at this kind of scratchpad that they showed here, really it's just a sequence of, copying the previous line from the input and doing some small modification on the input. Okay, so really it's almost like the model just repeatedly copies the previous line, but with some kind of small tweak or modification is imported for the execution of the algorithm. The second observation may be more interesting, and this is not a specific property of this addition algorithm, but really any algorithm can be written as a sequence of kind of modified copy operations, right? So I'll try to convince you in the next slide that this is kind of like a general property of any algorithm we can solve with a computer, is that we can write it down as a sequence of copying operations where we have small modifications between two lines. So the idea here is that any algorithm we can write as a Turing machine. So anything that we can execute on a computer, there's a Turing machine that can run the algorithm that we that we care about. And the idea here would be to convert this Turing machine, this kind of abstract model of computation that evaluates the function we want to compute, into a scratchpad, where each line of the scratchpad will capture the state of the Turing machine. So we'll write down the kind of Turing machine basically has each step of execution, it has a tape with the symbols on the tape. The head of the Turing machine is its some cell in this tape, and each step, depending on the state of the Turing machine, it can modify the symbol and move the head one step to the left or to the right. So we're going to encode the state of the Turing machine by writing down the tape, also, and the state of the head and the position of the head next to the symbol that the head is currently looking at. And if we do this kind of line by line, we would notice that just, because of the way that the Turing machine operates, this ends up being as a sequence of almost copy operation, where there's a small modification in the input sequence between one line and another, and this kind of is a very local modification only around where the head is located. Okay. Is this clear? Okay, and this mechanism is what we call the Turing program. So basically a way to convert any program or any Turing machine into a scratchpad where all the lines are almost identical with kind of small modification. So any algorithm can be written as a Turing program. And the question is, can transformers generate or learn to generate Turing programs? And we show a positive result here, showing a construction for a transformer that can generate Turing program using the construction is given by a RAS program. If you're not familiar with this, RASP is basically a sort of programming language that captures the way that the transformer operates. So in some sense, every line in this program is equivalent to an operation that a layer of transformer can do. So we show for any Turing machine, there exists a RASP program of size that depends on the for any Turing machine, there exists a RAS program with a number of lines O of n that can simulate the Turing machine of length that is exponential in this n. So n is kind of captures the size of the transformer that will need to execute this Turing machine, and the length of the execution grows exponentially with this size of the transformer. And we have some requirements. This Turing machine will run in memory, so it doesn't create kind of new memory beyond the input context. This is something that I think can be relaxed. And a kind of more important condition is that there are no repeated engrams in the input string, and that the machine does not create repeated engram during its execution. Okay, and this is important. Again, going back to kind of the previous part of the talk, since we're going to rely on this copying mechanism, it's important that we don't have these kind of repeated engrams in the context. Okay, so I'm not going to go into the construction specifically, but it's in some sense, on a high level, very similar to the copying construction. We're going to kind of construct a RAS program to do copying, and then instead of really just copying the previous kind of state of the machine, we're going to do a copying that modifies the state of the machine based on where the head is and all the kind of logic of the Turing program. Okay, so this is all kind of written in RAS, so you can actually kind of run this program in Python and execute it. And this is kind of, I think, the nice thing about these constructions. Okay, so just to show you that this is actually giving us some kind of non-trivial length realization results. So first, we're using these sort of Turing programs to get length realization on the addition problem. So this is already something that's been studied a lot. We're getting very, very good length realization, maybe not sort of like state-of-the-art length realization in this problem, but this is, I think, from training the model up to length 50, we can get it to generalize for over 100 or 120 digits, and it learns to execute this multi-digit addition algorithm step by step and generalize to longer strings. The next thing what we do, and this is much less studied. There's I think only maybe one work that gets length generalization results on this problem is doing length generalization on multiplication. Here we're varying one of the numbers. So there's n digit number multiplied by either one digit or three-digit number, and here again we construct this multiplication algorithm, kind of step-by-step multiplication with a multi-digit number. And again, we can see we can get length generalization results on this multiplication problem, both when we're multiplying with one-digit number and when we're multiplying with three-digit number. And this is, I think, showing that this method is kind of more general than just doing the scratchpad for the addition problem. Um, Finally, we're also training models to do SGD simulation in context. So this is a task that, to my knowledge, is we're the first to kind of show length generalization result in this problem. So we're basically giving the model in context a data set of inputs and ask it to kind of simulate the steps of the SGD algorithm on kind of small two-dimensional linear regression, and it learns to compute, given the kind of initial set of weight, it learns to compute the state of the weights that the SGD algorithm computes after every example, and returns the weight vector of SGD after all the updates are complete. And we can see that here too, using this kind of scratchpad technique, we can train the model to extrapolate to longer data sets. Now the x-axis shows the size of the data set that we train a model on. We train it up to length 50 examples that can extrapolate to kind of run this simulated SGD on up to length 90 examples. Okay. So to show that this is, again, I was claiming that this is, not just a specific property of a single, a few arithmetic tasks. This is kind of more general mechanism. We're showing that the model can learn to length generalize on simulating arbitrary Turing machines. So here we're generating sort of random Turing machines by sampling the Turing machines from kind of a random distribution. We have 5 possible states and 15 input symbols. We're kind of sampling the Turing machine by randomly choosing the kind of state transition and operations of the Turing machine each time from scratch, and we're randomly generating the state of the Turing machine and training the model to predict the next state of the machine. And here I'm plotting the, again, length generalization, where we're controlling for the length of the tape that the model sees. And again, we can see that we get very nice extrapolation on different Turing machines for when we're training the model to kind of execute this one step of Turing machine. And this sort of tells us that, for potentially any algorithm, we can come up with a scratchpad such that we can train the model to get length generalization in this scratch. Okay, so just to summarize this, and then I'm happy to take questions if you have any. So I showed you that with this concept of Turing programs, we can write any algorithm as a sequence of copy and modification operations. Since we've already studied the ability of transformers to achieve length generalization on copying, we can kind of expect that it also learns to length generalize on this Turing program scheme, where just instead of copying the inputs from copying the strings from the input as they are, we are doing this kind of modified copying operation. And this this means that we can kind of translate the line generalization ability of the transformer into line generalization, essentially any algorithm we care about. And we show a theoretical result that these Turing programs can be implemented by transformers using the RASP programming language. And I think that this really kind of unlocks new line generalization capabilities on tasks that people didn't study before, and maybe this kind of can potentially be a way to achieve line generalization on essentially any task, right? So anything you want to train a transformer to go beyond the training distribution and to kind of extrapolate to longer length. If you use this Turing program approach, you can basically achieve this if you're able to kind of construct a data set and decompose a problem into these sequence of simple steps. Okay, so this is that's the end of the talk. I'm happy to take any questions.